So if we notice where are the metals and where are the non-metals, we remember that it's a zigzag line that starts there, and if you ever want to know a good way to remember that, where's that zigzag line, just remember that aluminium is a metal and silicon is not a metal, and then just draw a line, draw a zigzag around that. Silicon is actually a semi-metal, which is why they use it in it's a semiconductor, so it's why it's used in microchips and so on. Anyway, the point is that all the metals are over here on the left, and all the non-metals are over here on the right.
Yep.
Now, we won't worry too much about this. Why is it a zigzag and not just a vertical line at this moment? That's a bit too advanced. But what we do notice, metals on the left, non-metals on the right, which means metals have a low group number. So if metals have a low group number, what does that mean? So the group number tells you how many electrons in the outer shell. And you can always try that out. If I drew a picture of lithium, I'd have 2 in the first shell, and then because it's 3 total electrons, I would have 1 in the next shell, which means the outer shell would have 1, and with sodium I'd have 2, and then 8, and then I'd have to have 1 in the next shell. So again, 1 in the outer shell, and you can keep doing this. Now, as you go further down, it does get a bit confusing, but that's because at GCSE you only learn the first, second, and third shell. And then after that, it gets quite confusing. You touch upon that in A-level chemistry. But anyway, so the main point is that metals are with a low group number, which means they have a low number of electrons in the outer shell. Metals have a low number of electrons in the outer shell. Non-metals have a high number of electrons in the outer shell. Clearly, again, it gets a bit confusing because why is it therefore that boron and aluminium, they both have the same number of electrons in the outer shell? Why is it that aluminium is a metal and boron is a non-metal? Well, we'll just not mention that at this point because it's, again, a little bit confusing and we don't need to know it in that much detail for this topic. Point is, low number of electrons for metals on the whole, high number of electrons on the whole for non-metals. So why is that relevant for ionic bonds and so on? It's because, well, we know that all elements, all atoms like to form full outer shells. So basically, metals tend to want to lose electrons when reacting. Okay, maybe it's probably true to say they always lose electrons. I think that would be true, but I'm going to just play it safe and say tend to. Metals tend to want to lose electrons, and then non-metals tend to want to gain electrons. Tend to want to gain electrons. So why is it that way around? Well, Steve, can you tell me why it's that way around? So they're both trying to form full outer shells. So metals it makes much more sense for a metal to lose the few outer electrons than to gain a ton of electrons. That's why. And by the way, depending on how easy it is to do that, will tell you how reactive the element is. So these group 1 metals are very reactive because they all need to only lose 1 electron. So whereas it'd be ridiculous for them to think about gaining 7 electrons, so that's why they lose electrons. That's why metals lose electrons, because they have a small number in the outer shell. It makes more sense to lose that outer shell than to fill up the outer shell. Non-metals, on the other hand, especially the most reactive non-metals, which is group 7, the halogens, have a nearly full outer shell. So it makes more sense for them to fill that outer shell. Okay, so that's what metals tend to do, and that's what non-metals tend to do. So that would mean that when a metal and a non-metal come into, when a metal and non-metal come into contact, and they would like to somehow bond, then it would make more sense for the let's say sodium, and we've got chlorine. The sodium would form a positive bond, and sorry, not positive bond, would form a positive charge because it would lose the one outer electron, and it would give that electron to chlorine, and chlorine would then fill its outer shell and be negative. So you can redraw this this sodium atom just by doing a circle and doing a circle and a little plus in the middle. So this is a bit confusing because sometimes this is the symbol for a proton, but really all it is, if you think about it, it's just a positive circle. So this positive circle is just my sodium ion, and then you'd have a negative circle, and this negative circle would mean my chloride ion, I should say. So that's my chloride ion. Now, clearly, they're going to attract to one another because similarly to magnets, a positive charge, something with a positive charge will be attracted to something with a negative charge. So they would form an attractive, they would be attractive to one another. Now, I'll just keep this last little bit in this video. If we had this would, well, let's have a think about it. So this is this one here is now formed positive charge because it's lost an electron. Therefore, it has essentially the wrong number of electrons, right? So the protons and electrons are no longer matched, and because of that, we call it an ion. So this has formed an ion. This has formed an ion. That's why we call this ionic bonding. So because when they're now attracted to each other. But one thing we do need to realize about ionic bonding is that we can't, and this is quite important, I think, actually, because so many people don't realize this, and I've come across a lot of people who don't realize this that really should realize it, in my opinion, but I'll know it in my opinion. And that is there are no such things. If there is no such thing, that's better. Is no such thing as an ionic molecule. You can't. So, well, why is well, it'll make it.
Covalent.
So first of all, you can have two different atoms bonded, and they don't have to be a compound. A compound would just mean that there'd have to be two different elements. So you could. So we're talking about well, first of all, ionic. Whenever there's an ionic bond, it must be a compound because there's two different elements, at least two different elements, because you've got a non-metal and a metal. So that would have to be a compound. You could have a covalent compound as well. But the reason why you can't form covalent molecules is, so let me just unlock that. Is because of this. So let me just I'll demonstrate it. I need to just group that. So if we had this one next to each other, they're now very happy because they are attracted to each other, that they're close to each other, and that's where they want to be. But the thing is, on the right hand side of that negative ion, the chloride ion, it would still attract to another positive ion. So it would be fine if a positive ion came into contact with that right hand side, it would be attracted to it, and also to the underside as well, right? And then in the same way, if a chloride ion came over here, it would nicely fit there because it's going to be attracted to these two positive ions. And you could just keep on doing this for forever, really, couldn't you? Just keep on adding them like that, and they'd end up forming a sort of a pattern that would just kind of, in the most simplest way, would be a kind of crisscross pattern, like a checkerboard or something. But you can see how this would just get more massive, and you could just. So if this was, that doesn't quite work, does it? spot the deliberate mistake. There we are. Let's see. If I take this one and put that there, that should be right, shouldn't it? Yeah. So basically, let's get that one as well. And we'll stop at that point. But you can see that we could just keep going on forever, right? Now, this is what we call an ionic lattice. Okay, so I'll just write that, just label that there, ionic lattice. So essentially what that means is we could just keep adding to it, and it would there's no real limit to how big that thing is. Whereas that's totally different to a molecule, which must be covalent. So if we think about a very simple diagram of a molecule, like water, for example. So water is an oxygen atom with 2 hydrogen atoms. If another oxygen atom came along, first of all, it wouldn't come along on its own, but if for some reason it did, it's not going to. There's no reason why it would join onto this oxygen molecule. There's no charge there. That's not how covalent bonds work. So that's what a molecule is, essentially a self-contained group of atoms that have fulfilled everything. They've all got full outer shells now, and that's everything. They're all complete. That doesn't happen with ionic bonds. In ionic bonds, it just can keep on going forever. You can actually have covalent lattices, right? But we won't talk about. We're not talking about that at the moment. So you can have a lattice, in other words, a sort of never-ending structure made of covalent bonds. You can't have the opposite in terms of ionic compounds. So we'll just stop the video just there, just to introduce